Okay, so hello everyone. Welcome to this workshop about uncertainties. So, as you probably know, because you probably read the abstract, what we want to do, it's really talk about uncertainties. So why are they instrumental? I guess that you all have already a good idea about that. So if you consider two parameters, X and Y, it can be any of your favorite measure. You all agree with me that if you just give one single point without anything else, that's bad because you don't have any uncertainty. So I mean, such a measure like that actually can be already very difficult to get. It can be a lot of work to already have a measure of any of your favorite parameters, but like that, it's meaningless. Because actually uncertainties are really a metric that allows you to to test models or theories, and also to compare your results to other data points. So that's a metric that is important. So if we assume that that's the probability distribution of these two parameters, then plotting error bars, actually, it's already something good. I mean, we can work with that. But one thing that we are going to discuss along this workshop is that actually uncertainties, it's not a single measure, it's really a set of information, and that is very important to actually, transmit them through different steps of what we do, and actually to other studies too. So here I give you another example. If you take into account correlations, you get ellipses, can get even skewed uncertainty ellipses if you get asymmetry, or even the full probability distribution of your problem. Because what I said. So what's also interesting and why we are talking about that here is because there are several particularities to ISM studies that make the subject of uncertainties, something that I think we should think about. So the first thing is that ISM studies often rely on a long chain of heterogeneous data using, laboratory data in some sort, observations, and also models, simulation, computations. And so I think the audience at this colloquium actually reflects this diversity. And I think that a lot of what we do actually really rely on these three things, even if we are not always aware of it. There may be some hidden, quantities that actually rely on that. And so what it means is that, and so that's not necessarily the same in other fields. There are some fields that are more self-contained. And so what it means that the uncertainties that are going to enter into these different fields are in some sort combined together, and we have to account for them. And it's not something that is trivial. The other thing is that what we study actually impacts the way we work. And so what I'm going to say after it's not general. I mean, it's not a generality, but it's a trend that I've noticed. And it's the fact that in ISM studies, we tend, compared to other fields like particle physics, work on relatively small samples in relatively small teams. And if you compare, for example, to people working on cosmology, they tend to work in large teams on the same data set, which is basically the whole sky. And so it means that by necessity, they need to have a standardized, reproducible uncertainty estimate, because otherwise they would be contradicting each other. While us, since we are more scattered, we can get away with it. So, for example, I show you one of these plots. That's the correlation between two cosmological parameters. See the omega m and sigma 8. And you see that in cosmology, they provide the full probability distribution of these parameters. And that's something that actually they can access to. They can refine using different sets of data. So they can really test the stress between different models. And what I noticed is that actually in the ISM community, often the people actually who have the most, who take the most care about the uncertainties are often people working on whole sky for the same reason as that. So, I mean, it's what I say, it's very general, and I'm sure there are special cases, and we can discuss about that, but I think there is a trend about that, and that was one of the motivations too. So here I'm showing you an example of what I was saying before, the fact that we often have nested uncertainty studies. So I'm taking one of my last studies as an example, briefly summarized. So recently I did a study where I looked at a sample of galaxies studied at multi-wavelength, from the UV to submillimeters. So those observations have uncertainties. All these instruments are cross-correlated between each other, so it means they have a lot of correlations. From that, we did some SED fitting. So it's a Bayesian SED fit, so it's relatively good to account for the uncertainties, but there are some assumptions made about the way the prior is parameterized. So there are some uncertainty about the hypothesis on the model. And the fact that the model that we used, the TEMIS model, is a model that is constrained on some observations, so which brings another layer of uncertainty, plus some laboratory data, again, some uncertainty, and it's designed to actually interpret observations of the Milky Way. And the question is that, can we also apply this model to galaxies that are very, strongly different? So that's another, you see, assumption about the model hypothesis. And we use that to constrain some chemical evolution. So that adds another layer of assumption about star formation histories, initial mass functions, and so on. And we use that to constrain the dust production by supernova yield. So you see, there are all these nested, intricate, different layers of uncertainties. And what I described here is that I think there are mainly uncertainties about experimental data, observational data, and about the assumption of the model. And so the objectives of this workshop, it's first to have a general discussion about uncertainties and their associated methods. And we are going to have a diversity of interventions, of talks. So I'm sure that everyone is going to learn a lot about that. The other thing is that we want to provide an overview of the way they are taken into account in different studies of the PCMI community, to have a kind of a state-of-the-art overview, and also to provide grounded examples so that we can have something concrete when we discuss something that can be actually quite abstract. And finally, eventually, one of the objectives would be to kind of give some momentum to some initiative that could lead to a standardization of the way uncertainties are taken into account and published in the community. So the program of the workshop, as you have probably seen, so after me, there will be someone who actually is the philosopher and who actually works right now on quantifying uncertainties in astrochemical models. Then we will have a first large session talking about how to quantify uncertainties in laboratory experiments, in observations, and also in the model assumptions. And then we will have coffee, but then we will also have another session about how to, once we have quantified, estimated these original uncertainties, how to propagate them through data processing and modeling and comparison to simulations. And we will finish by a discussion about how to really communicate these uncertainties and make sure that we don't lose too many information in the process of successive studies.